Hey guys, I'm Batu, and this is my lab 4. Quick intro. Using the given initial conditions, such as the K value of the spring, the mass of a mass, we want to calculate the path and compare it to the real version. And that's the purpose of this lab. So to achieve our purpose, I use Tracker on the video to get the position data for comparison, as well as VPython and initial conditions to develop a model to see how closely those two matched up. So our initial conditions here were that the K value of spring was 6.82 Newton seconds, the mass was 0.402 kilograms, the unstretched length of the spring was 0.123 meters, and the initial position as per the tracker data was negative 0.118 and negative 0.634. Okay, so a quick preview of the results. They were fairly accurate, where the model developed almost completely mimicked real-world behavior. The main physics ideas here were in the second law, where acceleration is directly proportional to the force and inversely to the mass, momentum principle, conservation of energy, the spring force formula, kinetics, and most importantly, the velocity update and the position update formula. So let's start on the lab. So this was a video that we were supposed to analyze, where I used Tracker to just get all the positions for the spring. Um, And okay, now let's take a look at how the programming was used to mimic that. And so I generated a computational model in VPython using the previously mentioned initial conditions, and then update the position by recalculating forces and keeping track of energy. And as you can see on the code on the right, we calculate the force gravity, force spring, given same formulas as in class. F net is obviously the sum of all forces. Updated the ball's velocity position given said forces, updated the springs length, and then updated all the energy so that we can graph them. And so this is the output of the code right here. And as you can see, the blue ball is our model, the red ball is the real data, and it's pretty much identical, except for, as you can see right here, it's a little off, but overall pretty close. And then here's the output in terms of the graphs. Quick overview of the energy graph. You can see that as force of gravity, let's say the change in gravity is negative, then our change in US is positive, and then the kinetic energy fluctuates between the two. Very interesting. And you can see in terms of our X and our Y data, the model almost like completely mimicked the experiment. So let's discuss. Obviously, we did obtain a model that was super duper duper close to the actual thing that happened, but obviously it wasn't exact, and it did not consider the mass of the spring because we assumed that the spring was ideal. So some what ifs and what does it mean? First one, if our model was the energy principle satisfied, and yes, if we go back, we can see that the delta was a straight line, and so there was no change in energy, and in other words, energy was conserved. And then for number 2, using our data and tracker, let's estimate the oscillation from the x position and then the y position. And so it was 1.52 seconds for the x and 1.475 seconds for the y, but they both should be ideally the same. And I think if the time interval was smaller, then we will be able to find the exact values where both of them are returning to normal, and that should correspond to the perfect value. Okay. Some error sources were not considering the mass of spring, assuming the spring is ideal, and then just a random error like clicking in tracker. Obviously, there's going to be some inconsistency there. So in conclusion, it is definitely possible to make a fairly accurate model.